Okay, in this lecture I want to go over very carefully how we go about assembling the global stiffness matrix once we have all the element stiffness matrices computed. So let me remind you where we ended last time. So previously we developed the element equations of motion in matrix form. Okay, and these equations looked as follows. We said there was a mass matrix. We'll call that M sub E, for just to remind you that it's the element mass matrix, times a vector, Ui double dot E, that's the nodal acceleration vector, plus Ke, which is our element stiffness matrix, times Ui, again with the E in front. This is our nodal displacement vector. Is going to be equal to F. I, again, this is at the element level. And I'll just remind you this could be a function of t, as actually can the accelerations and displacements. Okay, so but we'll just call this equation 1. Okay, now we want to focus on how do we, now that we have these equations for every, maybe we have 100,000 elements in the model, how do we go about assembling these into a global equation that we can solve? Okay, so now we're going to focus on how to assemble the element equations together to construct a global system of equations. Okay, so I'll just tell you broadly how we do that. Okay. Okay, so in some sense, it's a simple procedure, right? The assembly of the global equations just proceeds by summing the forces on each node from each element, okay? So I'll write that down. So the assembly of the global stiffness matrix, or let's say the global equations, proceeds by summing the nodal force terms for each in each element. Okay, and then what do I mean by that? Well, you note that each row in the matrix equations, the element matrix equations, corresponds to an equation on a single degree of freedom of a single node. Okay, so note that each row corresponds to a single degree of freedom on a single node. Okay? So the way we approach this is we begin with a zero stiffness matrix, begin with zeros in the entire global stiffness matrix. Okay? Begin by initializing the global stiffness matrix. We'll call it the global stiffness matrix K with no subscripts. So begin by initializing the global stiffness matrix as a zero matrix. And then we just proceed by adding each row in every element equation to the appropriate row in the global equation. Okay? So then we proceed by adding each row in the element equations to the corresponding row in the global equations. Okay? Okay, so that is the answer, but I think sometimes it's a little confusing just to see it written down. So let's go through a really simple example about how we go about doing this. Okay? So let's go ahead and consider an example of a simple truss subject to just static loading. Okay, and I'm doing that so I don't have to. Everything I'm doing in this example will pertain to the equations of motion, but I don't want to have to in a nitty-gritty write everything down detail, keep track of the mass and the stiffness matrices simultaneously. So we're just going to focus on developing that global stiffness matrix. Okay. So this is the problem that I've used in the past. So if you took a class from me in the intro class, you've probably seen something like this. So let's just consider a triangular truss element. Okay, something like this. We're not going to go through the entire process of developing the equations. I'm just going to give them to you. This will be a 3, 4, 5 right triangle, right? Okay, and we'll go ahead and fix. It doesn't matter for this particular example problem, but we're going to maybe use this example when we talk about applying boundary conditions. So we're going to fix that edge. We're going to put this edge here on a roller, and we're going to go ahead and put this corner here on a roller, and then we'll go ahead and apply a load P to it. We're also going to say that obviously the truss member performance depends on the quantity EA, if you remember that. The stiffness times the area, the cross-sectional area. We're just going to say that's 1 for this example. Okay, so this is the problem that we're interested in solving. And if I go ahead and move over to here, I can write the FE, the finite element model of this problem. So here I'm going to try this again. Draw my triangle. Hopefully it's as good or better as my previous triangle. Okay, and so let's go ahead and we'll talk about, let's label this element element 1. We'll say this element is element 2, and this element is element 3. Okay, and then we'll also say that this node, that's node 1. This node is node 2, and this node is node 3. Right? So we have a 3-element, 3-node truss problem. Let me also give you the degrees of freedom in this truss. So let me, okay, so our degrees of freedom on node 1 are in the x direction. We'll call that U1. And node 1 could move in the y direction. Obviously it's not going to, but we're still going to call it V1. Okay? And then 2 has 2 degrees of freedom. It'll be U2 and V2. And then finally, node 3 has 2 degrees of freedom, U3 and V3. Okay? Now, let me give you the element equations for each of the elements 1, 2, and 3. Okay, so I'm not going to go back, and you can go look up in a textbook what the stiffness matrix looks like for a 2D truss element. Again, this is an advanced FEA class, so I'm assuming you've at least seen that somewhere or can go look it up easily. Okay, so I'm just going to give you the element equations here. So for element 1, we have the following equation: 1/3. Obviously, it's 1 over the length there, right? So it's 1/3 times the quantity. This matrix, which the top row is all zeros. The next row is 0, 1, 0, -1. And I should also give you a coordinate system. So this is x and y. The third row here on element 1 is zeros. And the final row is 0, -1, 0, 1. Okay, so that term that I just wrote down is the stiffness matrix. So it's multiplied by my nodal displacements. In this case, the nodal displacements are going to be U1, V1, U2, and V2. Okay? And that's going to be equal to, F1, so the force on node 1 in the x direction, F1 in the y direction, and then F2 in the x direction, and F2 in the y direction. And I'm going to also put a 1 here to remind you in this pre-superscript form that this pertains to the element 1. Okay? So there's the equations for element 1. How about for element 2? Okay, element 2 is actually very similar. We have a length of 4, so this factor out here becomes 1/4. Try to write a little bit more compactly here. And so our top term is 1, 0, -1, 0. And then this row is all zeros. The next row is -1, 0, 1, 0. And then our final row is all zeros. Okay? If we go to element 2, we can see that we have the degrees of freedom on U1. So we have U and V1. We also have U3 and V3. Okay? And that's going to be equal to the forces. It'll be F1x, F1y, and then now F3x and F3y. And I'm going to put a 2 in as a pre-superscript to tell you that these forces are computed for element 2. And for our final element, element 3, okay, we have the quantity 1/5. Okay, and this next term is I just had to compute these for you. So just I'm going to write it down. I'm not going to speak through all of them. You can pause the lecture here and copy them down in your notes if you're taking notes on this lecture. Okay. Okay, so there's the matrix terms, and now let's go through quickly on the displacement terms. If I look at element 3, I see that I have displacement terms that look like U2 V2 and U3 V3. And then I have that equaling my force terms, which are going to be F2x, F2y, F3x, and F3y. Okay, and I'm going to put again the pre-superscript of the element, so these are for element 3. Okay. So I know this took a long time to set up, but if I'm going to walk through carefully each of how we take each of these 3 elements and assemble them into a global, I want you to have all 3 elements sort of at your disposal to work with. Okay. So now what we want to do is we want to assemble these element stiffness equations into a global stiffness equation. Okay. So let's write that down. Let's say we want to now assemble to a global system of equations. Okay, so the first thing we need to know is we first need to know what's the size of this matrix going to be, and you can see that's going to be defined by the degrees of freedom. So I have 3 nodes with 2 degrees of freedom each. It gives me 6 degrees of freedom. So I'm going to have a 6 by 6 global stiffness matrix. Okay, so I'm going to draw that here. Let's hopefully this is large enough so we can all fit on the screen. Okay, and let's see if I can maybe divide up into regions here. So I know I'm going to have 6 rows and 6 columns. Okay, so that's our 6 column, and it's going to have 6 rows. So what's this going to be multiplied by? Well, it's going to be multiplied by this vector, this nodal displacement vector, U1, V1, U2, V2, U3, V3. Okay, and you're free to reorder that as you feel like. If you want to put all the U's together and all the V's together, that's your prerogative. As I've written it here, this first column will correspond to U1, the second to V1, and so on and so forth. Just for reference when we start trying to write our equations out. Okay. And this global set of stiffness equations is going to be equal to, and this is now the F1x, F1y, F2x, F2y, F3x, and F3y, right? That's what our global equation is going to be. And I'm going to go ahead and I'm going to break that force term down in just a second, a little bit further. So I said we want to sum forces. So let's just go ahead and do that. So I see that my first row should be summing the forces on F1 in the x direction. And I look up at my 3 elements and I see that I have an F1 in the x direction in element 1 and an F1 in the x direction from element 2, and I don't have that in element 3. So I just need to look at elements 1 and 2. So now all I want to do is to sum those up, right? I want to be able to say that f1 of x must be equal to f1x from element 1 plus f1x from element 2. Okay? And I'll go ahead and close this off here. Okay, so you get that. Okay, so and how do we do that? Well, this first row is just the zeros. So if I look at this, corresponds to U1, V1, U2, V2, and those are all zeros. So U1, V1, U2, V2 are all zeros. Okay, and if I go over to element 2, I see that that first row corresponds to 1, 0, negative 1, 0. But now I have U1, V1, U3, V3. So here's that first term. Remember, I have a 1/4 outside. So this is going to be plus 1/4. And then V1, let's see, that term in the first row of element 2 is 0, so plus 0. And then in the next row, I don't have anything actually for U2 and V2, right? Those terms, those degrees of freedom don't exist in element 2, so I just move on. And I go to U3 and I see that the next term in the U3 component of that first row is negative 1 times 1/4, so this is going to be negative 1/4, right? And then 0. Okay, so that's my first row of my global system of equations. Now let's do the second. Okay, the second is going to be f1y, and we have the same because we have the nodes that are corresponding. They'll come from the same elements. So f1y of element 1 plus f1y of element 2. Right? There is no f1y in element 3. So let's go ahead and do that again. Do the same thing. So maybe I should draw a line across here so we can kind of separate out this easily. Okay, so there's the first row. All right, so the first term there in element, the second row now has the components U1, V1, U2, V2, and that first term is 0, so we have 0 here again. Okay, and the second term is 1 times 1/3, so this becomes 1/3. The next term is 0, and the next term is negative 1 times 1/3, so negative 1/3. Okay? And then I look up at element 2, and I see that in the f1y component, I get zeros entirely in the U1, V1, U3, and V3. So it's literally going to be plus 0, and then 0 and 0, right? So this is now my completed second row. So let's draw a line. Okay. Now let's do the next. How about f2x? And let's see where we have f2x. Well, we have that in element 1. We don't have it in element 2, but we do have it in element 3. So f2x from element 1 plus f2x from element 3. Okay? So let's see what that looks like. So f2x, that's the third row in this element 1 equation. And it's all zeros in the U1, V1, U2, V2. So we're going to write that. 0, 0, 0, 0. And now let's look at the f2x in element 3. Well, f2x in element 3 corresponds to the first row. And that's in the U2, V2, U3, V3 columns. And so we'll go ahead and just write that down. Okay, so U2 is going to be 0.64 divided by 5. There's a 1/5 out front. So it's 0.64 over 5. The next will be negative 0.48 over 5. The next term will be negative 0.64 over 5. And that last term will be 0.48 over 5. Okay? So that's all well and good. Now we're done with that row. Okay? Now let's go to the next row. So we know that we have the same nodes, so we have now f2y from element 1 plus f2y from element 3. Okay, so I go up here, f2y corresponds to the bottom row. Okay, so I look at that, and I see in my u1, v1, u2, v2 columns, that first term is going to be 0. The second term is going to be negative 1/3. And then I have 0. And then I have 1/3. right? So now I'm actually done. I've used up all of my elements from all of my nodes and nodal degrees of freedom from element 1, so I'll never come back to that again. But I go to F2y of element 3, which corresponds to, let's see, the second row. And those, remember, are in the U2, V2, U3, V3 columns that correspond to here. Okay. So nothing changes in U1 and V1, but now this term becomes negative 0.48 divided by 5. I have to add now the next term, which is going to be plus 0.36 divided by 5. And then I go here, there's a 0.48, so 0.48 divided by 5. And finally, there's a negative 0.36 divided by 5, right? So now we're done with row 4. We have 2 more degrees of freedom to go. This is going to now be F3x. And let's see, I see an F3x in element 2. And I have an F3x in element 3. Okay? So in element 2, my F3x term corresponds to row 3, and that's in the U1, V1, U3, V3. So there's my U1, V1 terms. So this is going to look like negative 1/4, right? And then 0. And then I go to my U3 term. That looks like 1/4, and then 0, right? Okay, so now I want to see my F3x term for element 3. That's the third row here, and that's in my U2, V2, U3, V3. So I go ahead and just write that out. This becomes negative 0.64 divided by 5, 0.48 divided by 5, and then I have to add this to the previous, so this is plus 0.64 divided by 5, and then minus 0.48 divided by 5. Okay, so we've got 5 of those done. Let me draw my line here. And now my final degree of freedom is going to be on node 3 in the y direction, so F3y. It's going to be the same elements, plus F3x of element 3. Okay, so F3y in element 2, that is the bottom row, which is all zeros in U1, V1, and in U3 and V3. And then I go to F3y. It's also the bottom row in element 3. So and this is actually in now U2, V2. So this term becomes 0.48 divided by 5. The next is negative 0.36 divided by 5 minus 0.48 divided by 5. And then finally plus 0.36 divided by 5. Okay, that's it. That is the stiffness matrix, the global stiffness matrix, and that's what this is, right? But this is the global system of equations. So, this is the assembly. So we have assembled the element equations into a system of global equations. Okay? Okay, let me give you just a general principle of what we did here. So here's a general principle as you try to think about how you might code this up for the code you have to write for the 3D elements. Okay, so general principle, the first one is that the force degrees of freedom determine the row, right, in both element and global. Maybe I should say rows, right? Because the element that it tells you in the row it tells you in the element isn't necessarily the row it's going to be in the global, but you'll be able to identify the row by the force degree of freedom. Okay, and the column is going to correspond to, all right, the nodal displacement degrees of freedom. Okay, so hopefully that may be tedious, but that walkthrough showed you how we go about assembling the matrix of a three-element problem. And hopefully you can do something like this. I'd encourage you, as you write your code, to do this. Use this as a check to make sure it at least does this right, and then you can move on with a little bit more confidence that you're going to assemble a more complex set of equations with probably larger element equations correctly. So hopefully that was clear, and hopefully you feel like you can code that up now.